Okay, wonderful. Thank you all. Okay, so maybe it's the coffee, but I am very, very excited to tell you about more modern data-driven dynamical systems. So remember, what we have here is any system that evolves or changes in time according to some structure or some rules. I thought I would give you an example of something that's not a dynamical system. So this is one of my favorite wood panels from the Louvre. This is static. This is not a dynamical system. So that's an example. But almost everything else in the world is a dynamical system. Okay? And we've been talking about kind of the basic challenges that we have in modern dynamical systems. Often we don't know the dynamics, or we can't agree on them, or they're not at a form that's particularly useful. Often they're nonlinear, so we need to find coordinate transformations that simplify the dynamics, and high dimensionality is always a key challenge. So again, please interrupt at any time, at any point in this. I have probably way too much material for one tutorial. I'll save some of it for the fluid dynamics lecture on Tuesday, some of the high dimensional stuff. But if there's anything you're particularly interested in, I'll spend more time on that. Okay? How many of you want to know about how neural networks are being used to simulate dynamical systems? Okay, good. How many of you want to know some of the more classic dynamical systems identification that people have been doing for the last 60 years with linear and nonlinear regression? Okay, good. How many of you like to see cool movies about chaos? Okay, good. Let me see, anything else that I might be missing? Okay, why don't I start then with just a fun little video on chaos, just to get you primed. So a lot of the dynamical systems that we think about are broken up into these different levels of complexity, from linear to weakly nonlinear to strongly nonlinear. And here I'm talking about systems that are chaotic. And so chaos means something very particular. A lot of kind of the popular connotation of chaos is that it is inherently random, and this is not true. So deterministic systems that are not random but strictly deterministic can exhibit chaos, like this Lorentz system. What I've done here is simulate an initial cube of initial conditions, a small cube of initial conditions, and I integrate them through the system. And you can see that very quickly, small variations in the initial conditions stretch and are amplified by these nonlinear dynamics until eventually they get smeared onto this Lorentz attractor. So this is actually where the butterfly effect came from, was this butterfly attractor. And you'll notice that these red curves actually stay relatively close together. They're at least on the same wing of the attractor until they get near this saddle point down here. And then they really stretch and fold and become very unpredictable. Okay? And so that's essentially the common mathematical definition of chaos, is that you have a very sensitive dependence of your future state on the initial conditions or parameters of your system. Okay, so if I changed the parameters of the system by a tiny epsilon, things would diverge. If I change my initial condition by a tiny epsilon, things diverge. And for short times at least, they diverge approximately exponentially until they get to the size of the attractor. Okay? Now there's a fun fluid dynamics connection I'll make on Tuesday. The Lorentz system was actually formally derived as a solution of the Navier-Stokes equations in the Rayleigh-Benard convection. So this was derived from convective fluid dynamic equations. And it was one of the great triumphs of data-driven modeling and kind of first principles modeling being tied together. So this is an example I give my students in class of chaos. I think this tandem double pendulum probably is the clearest explanation I have for sensitive dependence on initial condition. This is a pretty cheap setup that we built just for this, this teaching example. Okay, good. And I start them at roughly the same initial condition. And you can tell that actually for quite some time they agree and do pretty similar behavior. But then after a little bit of time, they diverge. And so even a small change in the mass or the initial condition will eventually cause this divergent behavior because it's a chaotic system. Now, interestingly, if I started it with lower energy, so I started it closer to the down position and let them go, they'll stay synchronized basically forever, okay, because it's essentially doesn't have enough energy to excite the chaos in the system. Now, this is very interesting. It's related to the presence of saddle points. So does everyone know what a saddle point is? Okay, a saddle point, roughly speaking, is a fixed point that has some stable directions and at least one unstable direction. So trajectories can come in, but they get flung away from this fixed point. Saddle points are essentially the fixed points that mediate transport in dynamical systems. So me walking, I told you I'm an unstable double pendulum. Pretty unstable. I'm a little bit more stable because I've had my coffee. I have a bunch of saddle points. If you linearized me about the standing up position, I would have a saddle point with at least 2 unstable directions. And in this double pendulum example, if I look at the first pendulum in the down position and the second pendulum in the up position, this is an unstable saddle point. OK, so this makes sense, because if I take this pendulum with the first one down and the second one up, it is a fixed point. If I perfectly lined it up, then it would stay there. And if I oscillate the first pendulum, it's stable in that direction. But the second pendulum, if I breathe on it, it's going to go unstable. So it's got one stable direction and one unstable direction in the linearized case. And so interestingly, you only get this chaotic divergent behavior if you start with energy above the energy of the first saddle point in the system. So very important. I don't think this is very commonly talked about, but essentially, I have this kind of system with different wells, and I have to have energy above the saddle point to really excite the fundamental chaos of the system. So that's why I started in the left angle position, because this one's twice as heavy as this one, and this has just enough energy that I excite the chaos, but they stay synchronized for a really long time. Okay. If you started it in the purely vertical position, they would diverge almost instantaneously on a coin flip. Half the time they'd fall the same way, half the time they'd fall separate ways. Okay? And this idea has been used for decades in space mission design. So it turns out that you have these saddle points. I'm going to call them rank 1 saddle points if there's only one unstable direction. We call that a rank 1 saddle. Very, very important. Your DNA unzipping can be modeled as a rank 1 saddle system. All of the Sun, Jupiter, Sun, Saturn, Sun, Earth systems, the Sun and one planet, they have 5 fixed points, these Lagrange points that have been known for a long time. And a number of them are rank 1 saddle points. And so what they do is they provide very efficient transportation routes for the solar system. So if you want to get from one point to another, this is an artist rendition of this interplanetary transport network that's mediated by these rank 1 saddle fixed points. And also Jupiter has these saddle points between Jupiter and each of its moons. And so essentially, if you, I'll draw a little picture because I find this fascinating. I wasn't really planning on talking about this, but it's one of my favorite things to talk about. So if you have the Sun and you have Jupiter, and there are some fixed points, I'm not going to draw all of them, I'm going to draw these two. Let's say you are an asteroid or a spacecraft, and you have a certain amount of energy. This is in the frame that rotates with the axis of Sun and Jupiter. There is a potential energy landscape that's forbidden, given by this bumpy surface here. So I can't live in this white shaded region if I have a certain amount of energy. And if I have increasing energy, this white shaded region gets smaller and smaller and smaller. So if I'm an asteroid and I want to enter the inner solar system, I have to make a transfer around these rank 1 saddle points between the Jupiter and the Sun. And so it turns out that Jupiter is actually protecting us from distant objects, and so is Saturn. It's filtering out a lot of the space junk in the outer solar system, protecting the planets on the inner solar system. It also is pairing up asteroids. So it turns out that when we observe asteroids in the inner solar system, they're very often in binary pairs orbiting each other, which is weird and unexpected. You wouldn't expect there to be 10% of the asteroids in binary pairs. I don't know what the exact number is, but it's a lot. And the thought is that because so many objects have to come in through this, this pairing process, they actually get paired up and stay close together. So it's this weird gateway, these turnstiles, these revolving doors of how you get into and out of the inner solar system if you have a certain energy level. And so if you're a spacecraft that's energy limited, you're going to want to hop through these transportation networks to save fuel. Anyway, saddle points are interesting. Instability helps you travel efficiently. And you see it across basically everything. Fighter aircraft, humans walking, animal locomotion, space mission design, fluids, chemistry, like saddles do everything for us. Okay? But I don't want to give you the impression that everything is chaotic. So when I was an undergrad, I studied things like the three-body problem, and I was always amazed at how much rich and chaotic behavior comes out of these very, very simple equations. And in fact, Poincaré proved that there is no general solution to the three-body problem. There's not enough blackboards in the world to write down the solution in general to a three-body problem because it's chaotic. And so when I went to grad school and studied fluid dynamics, which is a much higher dimensional system, I thought that there's no way that a high dimensional nonlinear system can be anything but disordered and chaotic and really messy. But it turns out often, if you have high dimensional systems with weak coupling between the elements, order and patterns emerge. So I'm going to show you another example of a high dimensional system that is not chaotic. Good. So these are a bunch of metronomes. Maybe I will try to plug in, because I think the sound is pretty cool. OK, so someone has put a bunch of metronomes on a very weak board. So they're all out of phase and out of synchrony. But they're on this weakly coupled plastic board. You saw it shaking a little bit at the beginning. Now it's only very, very small motion. And already you can start to see that there's a lot of synchronization happening. There's almost a phase change that occurs in the system. I think there it is. It happened. Now, they're not all perfectly synchronized, but this video creeps me out a little bit. I think it should creep us all out. Yeah, if you want to do it, like just take 2 Coke cans and a plank and put 2 metronomes on it, and they'll synchronize. Just the little sloshing of having it on 2 Coke cans will do it. So they're all in lockstep. And notice this guy here. He's my hero. So the moral of the story is that oftentimes high-dimensional systems have emergent behavior, synchronization. Weak coupling between systems that have their own strong dynamics will often cause synchronization to occur. This is a 4-minute video, and eventually he gives in, or they give in to this peer pressure. So it's really, it's an interesting, I don't think we to this day really understand when and how structures and patterns will or will not emerge. We have rules of thumb sometimes, but it's not, so just be aware that oftentimes patterns come in, oftentimes things are disordered and chaotic. OK, good. So that was just kind of a fun little aside on chaos. Now I'm going to talk about data-driven dynamical systems. And I'm going to walk through a number of the most prominent techniques that have been developed in the last 10 or 20 years to identify dynamical systems from data and identify coordinate systems from data. This is an extremely biased view of the world, kind of myopic to what I think about on a regular basis, but this will give you an idea of the kinds of things that are commonly done. So I'm going to talk about data-driven dynamical systems where you have high-dimensional data, for example, neuroscience data. This is my wife's data, fluid data, climate data, and this is the spread of polio in Nigeria. So very interesting data from Josh Proctor and the Institute for Disease Modeling. And remember, we have these. What I'm going to talk about now is when equations are unknown. Okay. OK, so how many of you have heard of the dynamic mode decomposition? How many have not heard of the dynamic Beautiful. I love it. I love having 2/3 that have not heard of something that I'm going to talk about. So the dynamic mode decomposition is a technique that was developed in the fluid dynamics community in 2008, 2010 by Peter Schmidt. And very soon after, it's been applied to nearly every field of dynamical systems where there's high-dimensional nonlinear data. Okay? And this history is going to be incorrect and abbreviated. There have been things like the dynamic mode decomposition in climate science since decades earlier, but they didn't call it by that name and they didn't have the same interpretation. So I'm just going to tell you the story about dynamic mode decomposition. Okay, so the idea is you have data from a dynamical system, and remember, dynamical systems are always movies. They're not pictures, or else they'd be, not dynamic. So you have a movie of your dynamical system. In this case, it's just fluid flow past a cylinder at low Reynolds number. You see this in the clouds over mountains sometimes. And what we're going to do is take this system, the state of the system is basically given by the fluid vorticity at each of 100,000 grid points. That's how we simulate this fluid flow. I discretize space into 100,000 elements, and then I simulate the rules, the governing equations of how the fluid flow and those elements evolve in time. And so what I can do is I can take my movie and I decompose it as a series of snapshots in time. So these are just images evolving in time now. And then what you can do, we often get this data from experiments. So this works very well with experimental data. You don't need the governing equations. You could literally collect a movie from a camera, and you could shape those images as a sequence of images in time. Okay? And so then what you do is you reshape each of these high-dimensional fields, which are either 2D or 3D, into extremely tall, skinny vectors. In this case of size 100,000 by 1 at time 1. So this is my state at time 1, at time 2, at time 3, and so on and so forth. Okay? And I build another matrix x prime where I take the exact same data but shifted one time step into the future according to my dynamical system. Is everyone with me so far? I think I probably should not show. OK, good. OK, is everyone with me so far? Does anyone have questions? I take a movie, I take every image, I reshape it as a tall vector, and I stack them in columns of a matrix. Simple, OK? And now we're going to try the simplest thing in the world, linear regression, which if you ask some people is artificial intelligence. So what we're going to do is we're going to take these columns and we're going to try to find a best fit linear operator that evolves x to x, x1 to x2, x2 to x3, x3 to x4, and so on and so forth. We're going to do a least squares linear fit to find the best A matrix that goes from column to column to column. And specifically, because I built this time-shifted matrix, I'm going to try to find the A matrix so that AX equals x prime. Now, that's a kind of a ludicrous thing to hope to find, is some linear matrix that captures this nonlinear evolution. But bear with me for a minute. Everybody does it, so it must be OK. So what we're going to do is essentially build this A matrix as a least squares regression. This is the pseudo-inverse x dagger. To find this least squares best fit A that maps my data from time step to time step. OK? And in this matrix A has the size of my flow field by my flow field. So it's gigantic. And its eigenvectors have the size of a flow field. I can reshape those really tall, skinny eigenvectors into things that look like flow fields, things that look like the state of my system. And those eigenvalues are going to be like normal eigenvalues. They're going to have oscillatory components. They're going to have exponential growth or decay. They might be constant in time. And so what I get if I do the eigendecomposition of my best fit linear operator that advances my system, this is basically a linear dynamical systems model to fit my evolution. And the eigenvectors are eigenflow fields. And the eigenvalues tell me how those flow fields oscillate and grow and decay in time. And if I multiply this by this in time, this is a spatial mode, this is a temporal mode. If I multiply this by this and add these up, I reconstruct a movie of my flow field very accurately with maybe 6 modes. Pretty amazing. I get a 6-dimensional dynamical systems model that is linear, and it describes this fully nonlinear fluid flow equation. Very interesting. Okay, so everyone got really excited about this dynamic mode decomposition. There's a lot under the hood here I'm glossing over. Because I mentioned, let's for argument's say that this fluid flow field is described by 1,000,000 states. So my vector is 1,000,000 tall. So it's easier for me to say 1,000,000 than 100,000. Then this A matrix is 1,000,000 by 1,000,000. So first of all, you don't want to compute it. And second of all, you don't want to do its eigendecomposition. So the actual dynamic mode decomposition, a la Schmidt and Tu and others, what it does is it essentially uses singular value decomposition and dimensionality reduction to approximate the leading eigenvalues and eigenvectors of this A matrix without ever actually constructing it. So I'll walk you through what that looks like just a little bit. How many of you are pretty familiar with the singular value decomposition? The SVD, it's incredibly important. It's used everywhere. It's used for principal components analysis, dimensionality reduction. It's our go-to method for linear dimensionality reduction. Okay, and that's what we're going to use here. So the first step is, again, take the singular value decomposition of my data matrix X, U sigma V star. This is just the singular value decomposition. I can compute the pseudo-inverse of X easily because U and V are unitary matrices. So their inverses are their transposes. So if I want to invert V, I just multiply by V transpose, and so on and so forth. But remember, I don't actually want to build that gigantic A matrix. So what I'm going to do is I'm going to take these are my principal components, essentially, of my flow fields. These are my eigenflow fields. I'm going to pick the first 10 or 20 out of my first thousands that I have to choose from. So I'm going to pick the dominant 10 or 20 eigenflow fields. And what I'm going to do is project my A matrix onto this 10-dimensional subspace. And what I get is a little 10 by 10 matrix A, tilde. Now, this is a fun property of math that A tilde, the eigenvalues of A tilde will also be eigenvalues of A. And so I can compute this very, very cheap, efficient eigendecomposition to get my dynamic mode eigenvalues, lambda. And then I can use these little 10-dimensional eigenvectors to reconstruct my original data to get high-dimensional DMD eigenvectors. Now, I'm glossing over a little bit of details here. Big picture is, I found this best fit linear operator A, but I didn't want to actually solve for it or write it down. So instead what I do is I work with this proxy A tilde that's projected onto a dominant low-dimensional subspace of principal components. I just do PCA on my data, and I project it onto the dominant principal components. And then from the eigendecomposition of this tractable A tilde, I can obtain my eigenvalues directly, and I can get my modes by just recombining my data X prime in a certain order. Very useful, okay? And so these are my eigenvalues. These are my DMD modes. And they have a very physical interpretation. So this is a highly interpretable model in the sense that there are only a few modes I have to care about because my singular value decomposition hopefully has low rank structure, meaning there's only a few dominant patterns in the linear subspace of my data. And also, each of the eigenvectors has the shape of an eigenflow field, and so I can look at the structures that are evolving in time, and they have meaning to me. Okay, good. So this is a figure I shamelessly stole from my wife. This is essentially, so she works on DMD also. She thinks of DMD as essentially if principal components in space had a baby with Fourier transform in time. And these are two of the most important algorithms in the last 100 years. So it's no wonder that DMD is getting a lot of attention for modeling dynamical systems. So you're somehow simultaneously doing a dimensionality reduction in space and some kind of simplification in time. Okay, any questions anyone would like to ask about DMD? Yeah?
So if you were to move you have this flow going on. If that were to move up a little bit, would the order of the eigenvalues change? It's not obvious to me that everything will always be in the same place, the index of the eigenvalues and eigenvectors over time.
Yeah. Well, so I always choose my data to be sufficiently long that I capture the kinds of behavior I would be expecting to see. So okay, there's a lot of assumptions. I've shown you the case that works. I started on the case that works. This doesn't work to capture transients at all. So if I accelerate the flow a little bit, or I turn the cylinder, or I move it up, or I do anything at all to introduce a transient that would then die out, this fundamentally can't capture that. Okay? This captures periodic and quasi-periodic attractor behavior in low-dimensional systems, period. Okay? Yeah?
A simple question about how does it depend on the number of time steps?
Yeah, so you want the time between these to be small enough that you capture all of the relevant frequencies. And then in this kind of example, I want to sample for at least one full period, hopefully more, so that you can kind of average over it. Now, there are some pretty remarkable properties. If you have very clean data, you can actually sample less than one period, and you can actually get pretty good approximations to the low frequency behavior. Not completely well understood, but Jonathan too looked at this a lot in his thesis. Yeah. Yeah, so this is related to something called Koopman operator theory, which I'll talk about next. And just now, our group and Igor Mezich's group and other groups are starting to uncover what you would call an uncertainty principle for Koopman systems in the space-time decomposition. Okay, so since not everyone works with the singular value decomposition, I want to make some moral comments, maybe moral judgments, I don't know. You have a system, some state of my system U. This is a high-dimensional vector, my flow field, x, whatever. And it's a function of x and t. And fundamentally, what you're trying to do in the singular value decomposition and the dynamic mode decomposition and lots and lots and lots and lots of decompositions is you're trying to say that this is a sum of some spatial modes times some time series. I want to add up R of these things, where R is a small number compared to the dimension of U. Okay? This is what you call a space-time separation of variables. If you took ODEs, it's one of the first things you learn to solve ODEs is separation of variables. That's how you solve the heat equation. Okay? Not a good idea for traveling waves. I'm going to talk more about this later, but space-time separation, I pissed off my students once because I gave them a traveling wave problem. I told them solve it with separation of variables on an exam, and of course you can't do it. And it's a bad exam problem. And so it's a bad step 0 or step 1 for traveling waves. And so I'll pose to lots of you as an open question, and it's starting to get resolved with convolutional neural networks. And we'll talk more about this on Tuesday. We should probably stop assuming we have a space-time separation of variables for systems where we clearly don't, because it's just an inefficient representation for systems with traveling waves. I'll give you an example, very simple example. This is an experiment I did in my office at UW. I took my iPhone, I put a ball on the desk, and I rolled it across the desk. So it's rolling across the desk from here to here. And I do dynamic mode decomposition on this movie. How complex is this scene in your mind? How much stuff is going on in this movie I described? One thing happening. There's one ball, and it is moving at one speed. Okay? SVD, singular value decomposition, and dynamic mode decomposition needed dozens of modes to describe this behavior because it's approximating this using a Fourier series. It's trying to add up this linear translation with a Fourier series of a bunch of weird eigenballs. And what's worse is when I take my model and I run it forward in time past where I collected the training data, so I can actually reconstruct the video perfectly, machine precision. But guess what happens when I go a little bit farther in time? My future state prediction tells me it reverses direction and goes right back because it's spanned by these sine waves. So the support of this model is from here to here. It doesn't know that physics goes that way. So there's fundamental problems with these space-time. You have to be careful in how you apply these methods. Okay? Okay. But it's been an extremely useful technique in fluid dynamics. So I love this paper. I think you all should read it. Peter Schmidt is one of the authors, where on page 15, in the third paragraph, you'll find a sentence that starts a whole research direction. Okay, so excellent paper. He applied this dynamic mode decomposition to interesting canonical flows, complex flows that have dominant periodic or quasi-periodic structure, like flows over a cavity. It's a little hard to see here, but basically you just have a step and the flow is oscillating. It's kind of like a whistle. Okay, and this is a very periodic system. Also things like jets and other things. Very soon after, Clancy Rowley, Igor Mezich, and others made a strong connection between the DMD and this notion of Koopman operator theory. How many of you have heard of Koopman? How many haven't? Okay, I'm going to talk about Koopman in the next segment. But basically, they gave a theoretical foundation for why sometimes you can describe nonlinear systems using these extremely oversimplified linear approximation techniques. Okay, so the original paper derived the algorithm and showed how to use it on data, and this paper connected it firmly to dynamical systems theory. And this is a video, again, I took for my wife. She makes great videos, where basically you have a high-dimensional noisy signal. Like, okay, again, how much stuff is going on in this movie? Looks like two things-ish, right? There's a Gaussian, big Gaussian, slow, and there's a little square, fast. And then there's a bunch of crap on top, okay? But it's basically two things happening. So if you do principal components analysis, or if you do the singular value decomposition naively, what you get, you do find that it's essentially a rank 2 system. There's two modes that have energy and everything else is noise. But these are the two modes. And essentially what it's doing is it's mixing these, this has energy, and this has energy or variance in the data. And the mode 1 and mode 2 mix these two structures. And so what the dynamic mode decomposition essentially does is it finds a linear combination of these that separates them out by time scales. That's that Fourier transform in time. And so when you do the, I guess I should show you ICA. Actually, ICA does a pretty good job in dependent component analysis, but it does keep a lot of the noise in the Gaussian term. And essentially what DMD allows you to do is it separates out, by finding a linear combination of these principal components, it separates out these two structures by their time scales. And importantly, it actually gives you an eigenvalue. So you have a model for how this evolves in time. This case works because this is separable in space and time. Nothing's moving, nothing's translating. So this is a case where continuous symmetries are really hard to incorporate into the data-driven method. That's an open challenge right now, is how do you incorporate a continuous symmetry like translation or rotation into this DMD framework? It works well when nothing moves, when each pixel means the same thing for all time. If my square moved across, this wouldn't work anymore. Okay? And since being introduced, this has been applied to a ton of systems. This is an old slide from like 2017 or 2016, 2015, I don't know. I think I was at United Technologies. And so since then, there's probably 10 times more applications: robotics, social networks, plasma physics, financial markets, you name it, someone has applied DMD to that time series data. Okay? Okay, any other questions about DMD? The Rowley paper. Yeah. Yeah, so 2009 JFM Rowley. Yep, very, very good paper. Okay, so that, yeah, Frank.
It's worth mentioning that the TICA is essentially the same
as DMD.
DMD, or not exactly, it's more like eDMD, but
yeah, so I'm
a lot older and known in another community.
So this is a common theme in DMD, is every major innovation we find in DMD has been done before at least a decade or 5 years in other fields. There's a really good review paper on this, the one where you compare TICA, DMD, eDMD, 2017. Do you know the paper I'm talking about?
I think it's our paper.
It's your paper, and yeah, who's the first author? Is it Kloos? You think you know it. So there's a really interesting 2017 paper by Frank and others essentially comparing all of these methods historically. Yeah, Stefan is the first author. And also the Jonathan Tu Journal of Computational Dynamics paper compares DMD to classic methods in climate science and control theory, and these go back to the 70s. So yeah, I'm telling a very abbreviated version of history here. Okay, so I started off with discovering dynamics. Remember that DMD, part of what makes it so useful is that you don't need any governing equations. I didn't need to know the Navier-Stokes equations. I didn't need to know F equals ma or any equations at all. I just needed a movie. All you need is a movie, and you can apply DMD. Okay. The other thing I'm going to talk about now in this kind of next bit is on discovering coordinate systems. So half of the problem is discovering the dynamics, assuming you don't have governing equations. The other part is going to be about discovering coordinate systems that are effective, that simplify my system in some way. Okay, so now we're talking about this idea of nonlinearity. And in particular, we're talking about coordinate transformations that linearize our dynamical system. And I've already mentioned that most of the huge advances we've had in fundamental physics over the last hundreds or thousands of years have centered around the choice of coordinate systems. Okay? Relativity is a choice of coordinate systems. Kepler and Newton were based on a choice of coordinate systems, right? The heliocentric coordinate system. Fourier essentially developed a coordinate system to linearize and simplify the heat equations. And so I think of the Fourier transform as probably the model of what we're looking for in a coordinate transformation. Fourier transform is a space-time separation of variables if you apply it to this kind of data. The SVD is a data-driven version of the Fourier transform. You can think of principal components on that kind of data as just data-driven Fourier. And what's happening now that we have these very powerful representations in deep learning, like what Frank was talking about, we're starting to be able to go beyond those kind of linear coordinate transformations, mathematical from Fourier, data-driven with SVD, and now we're starting to get into more complicated nonlinear coordinate transformations designed to simplify the dynamics in a certain way. Okay? And it's interesting, the theory of these coordinate transformations to linearize dynamics actually goes way back to Bernard Koopman in 1931. So there's all kinds of interesting history I could tell you about Koopman, intrigue.
It's not attributed to Koopman in the 29 paper of von Neumann.
I think von Neumann's paper was in 31 or 32. It was in January of 32, and Birkhoff's was in December of 31. He scooped him by 1 month. Very interesting, interesting history. I encourage you to read about it. In this paper, Hamiltonian Systems and Transformations in Hilbert Space, essentially what Koopman said, and I'm going to paraphrase terribly, is that if you have a nonlinear system in terms of a state, if instead you think about the evolution of the Hilbert space of measurement functions you could measure the state with, that evolves linearly along the dynamics. So if you take your state, which is finite dimensional usually, and you lift to this infinite dimensional Hilbert space of all possible measurements I could take of the state, the dynamics in that measurement space are linear. There's a linear operator that evolves that in time. And so it's this trade-off you get to decide, do I want finite dimensional, which is nice, but nonlinear, which is hard? Or do I want infinite dimensional, which is hard, but linear, which is nice? So it's this trade-off. Okay? And it is a very, very interesting history. I'm going to point you to, so Koopman, his paper, at the time, he wasn't thinking about coordinate transformations to linearize systems. I don't think. That wasn't, I don't think, his main motivation at the time. Very soon after he wrote his paper, von Neumann and Birkhoff independently were able to solve Boltzmann's ergodic hypothesis, which was one of the landmarks in dynamical systems. It's one of the most important math papers of the last century, and it tied up Boltzmann's statistical mechanics theory with a nice bow. Okay? And there's a great history I would point you to in PNAS by Calvin Moore that essentially talks about the development of this theory, how Koopman's paper was important, and the various intrigue that happened. Basically, I think Koopman was a former PhD student of Birkhoff, and Birkhoff basically scooped von Neumann. This was the first paper von Neumann wrote in English, was the proof of the ergodic hypothesis. So he was just fresh at Princeton, young guy, very interesting story. Anyway, this Koopman operator theory has been recently revamped. A lot of the work by Igor Mezich since the late 90s until now, and others, many in the room, Frank's group, our group, and others, have been kind of revitalizing this Koopman theory. Because when I say that I can take a nonlinear system and make it linear by considering how it operates on measurement functions, when I say measurement, you should think data. So now that we have vast and increasing amounts of potential data that I collect from systems, this idea of building linear models in data space is much more plausible. So Koopman, I believe, has had this revitalization in the last 20 years because of the vast and increasing amounts of data and computational power that allow us to get towards this infinite dimensional representation. OK, so I've kind of talked around the issue for a while. What I'm going to do now is just show you an example of Koopman working to hopefully get you motivated that it can, in fact, work. OK, sometimes I show math slides first, and it usually confuses everyone. So I'm just going to start with a super simple example where it works. Yeah?
A very stupid question. So since the people you mentioned, where they talk about quantum mechanics, unitary operators, this is what they had in mind? Because 1931.
Yeah, so it's a few years after Heisenberg. This was definitely I don't know how to answer your question because I'm still reading the history. This is in my spare time. I'm trying to figure out how this was pieced together. Certainly, the operator theoretic perspective was emerging, and von Neumann, of course, was instrumental in redefining, redefining physics in those terms around that same time. I can't really give you a good history, but I would like to. I wish I knew more about it. OK, so I'm going to walk you through a very simple example of what I mean by Koopman theory. So it's a coordinate transformation where things become simpler, linear. So we're going to look at this little two-dimensional dynamical system. It is nonlinear, so you can see that it has this little x1 squared. That means it's nonlinear. And it has a single fixed point at the origin. So the only fixed point of the system is at x1 equals 0. And if x1 equals 0, then x2 has to equal 0. That's the only fixed point. So it has a single fixed point here. And I'm going to choose the lambda eigenvalue to be much faster, much more stable than the mu eigenvalue. And what that means is that x2 will very rapidly be forced to equal x1 squared on a fast time scale. That's what it means if this is a really stable negative eigenvalue. So if I start with these initial conditions, very rapidly they attract onto this parabolic manifold, this red manifold, given by x2 equals x1 squared. And then slowly, the x1 variable will walk them towards the origin. It's a stable system, single fixed point, slow manifold. OK? And so what you can do is build an augmented state. Again, remember, we're going from our state to some higher dimensional version of the state, measurements of the state, that include the original state x1 and x2, along with x1 squared, some nonlinear function of the state. And what I'm going to show you is that in these coordinates, I can represent this system as an honest-to-goodness nonlinear dynamical, linear dynamical system. So let's just go through the math. It's super simple. OK, y1 dot, so it's the same as x1 dot, and it's mu y1. OK, y2 dot is x2 dot, and it's lambda y2 minus lambda y3. So that equation became linear. And everything hinges on this last y3 equation. This is the crux. y3 dot is ddt of x1 squared, which is 2x1 x1 dot, which is 2 mu x1 squared, which is 2 mu y3. So that term is also linear. Everyone follow what happened? Pretty simple, right? Just chain rule. And so by augmenting the dimension, and this is the phase portrait. These are the curves. These white curves are the actual trajectories of this linear system, e to the at. in 3-dimensional space. And when I project them down, I recover everything about my original system. Now again, I am showing you this example because it's the one that worked. Okay, this is one of the only ones that easily works. And then what you can do is you can look at the eigenvalues and eigenvectors of this matrix, and you can find a simpler set of eigenfunctions, if you will, that behave linearly if you only measured in those eigenfunction directions. So if I measured this function phi lambda, I would appear in that reference frame that my dynamics were just e to the lambda t. Okay? And so that's really what we're trying to do, is we're trying to find these special functions that if I viewed the world through those lenses, everything would become linear. Okay, simple idea, but let's try it on a system that also should work. Maybe should, I don't know. It's a simple system, x dot equals x squared. So in some sense, this looks even simpler, right? Anyone know what this is characterized by? A hint, you can't say it in the airport. You can't talk about it. It blows up in finite time. So x dot equals x squared will blow up in finite time. So it is actually nastier. It's not as simple of a system. But let's try the exact same trick. Let's try to linearize this by including the nonlinear term in the dynamic. So what I'm going to do is I'm going to augment my state to include an x squared term. And we're just going to go through some basic math here. So ddt of y2 is 2x x dot. But since x dot is x squared, this is 2x cubed. Shoot. So it doesn't close. I don't have an x cubed in my span, so I'd have to tack on an x cubed. But then ddt of x cubed is 3x squared x dot is 3x to the fourth, and I'd need an x to the fourth. So I tack on an x to the fourth, and it never, ever ends. It never closes. You get into this fundamental closure issue that no matter how many polynomials are a terrible basis, by the way. But if you chose polynomials like I did, because that's what the dynamics had, this would never, ever close. And you now see where Koopman was coming from, that you actually need the actual infinite dimensional representation for this operator. It doesn't close in any finite dimensional polynomial representation. You had a question first? No? Yep.
Does this one even have discrete spectrum?
Great question. There's definitely a discrete component. I don't know if it has a continuous component as well. That's a really good question. I don't know the answer to that. And it's kind of interesting. If I was just a naive data person, I would just chop this thing off at rank 4 or rank 5 or rank 6. And actually, it does get better and better for a time. Like you could certainly use this for prediction or a model predictive controller for a while. But it's not satisfying to me. Marina.
You showed us the phi lambda line. Is there a theorem saying that there are always two functions that
Oh, that's a great question. So there are now theorems on principal eigenfunctions of the Koopman operator that then generate all of the other. So there's super weird stuff with Koopman. So the question is, in the last example, the one that actually worked that had a discrete set of eigenvalues, there were kind of two eigenfunctions, phi mu and phi lambda, that I determined. And phi mu, if I looked at ddt of phi mu, it would act like mu phi mu. It would be a linear system in that coordinates given by mu. But if I have phi mu squared, and I take ddt of it, I'm pretty sure I'm going to get 2 phi mu lambda mu phi mu equals 2. So phi mu squared is also an eigenfunction, and phi mu cubed, and phi mu to the n, and weird things happen. So you essentially get a lattice of eigenvalues and eigenfunctions at integer spacing of your basic mu and lambda eigenvalues. And so the question is basically how many of those fundamental eigenvalues, lambda and mu, do you have for a system? There are theorems. Igor Mezich has some theorems. I believe Shai Rezin has some theorems about these principal Koopman eigenfunctions. But it's still, I don't say, completely resolved that I understand. OK. So I remember showing this to Clancy Rowley a number of years ago. We were sitting in a lobby in Tallahassee, Florida, early in the morning before our coffee. And I said, hey, what do you make of this? This seems like a problem with DMD and Koopman theory. And so Clancy wrote down on a napkin the eigenfunction for this system. Phi of x equals e to the minus 1 over x. And it turns out, if you look at the system through this world and compute its derivative, it does in fact equal phi x. So it's eigenvalue 1. That is an eigenfunction of the Koopman operator. Okay? I'm convinced now that he's thought about this system before. Maybe I'll ask him next time I see him. But you certainly can write down eigenfunctions even when a naive basis fails. There are these special functions where things become linear in this function. They might be hard to find. This is what my wife calls the Feynman trick. You scratch your head and you write down the answer. Doesn't work for high-dimensional systems, for complex systems that we all deal with. So you need kind of a data-driven way of finding these things. Okay.
That probably answers my question. You can put a lambda there, and then it will be, you have all the.
Yeah, I think that's probably.
Square integrable, so that's.
Yeah, in principle, that shouldn't. Yeah, exactly. So I'm probably going to kind of skip over this. Basically, the point I'm trying to make here is that what you want in practice, I don't like working in infinite dimensions. Makes me tired. My computer certainly doesn't like working in infinite dimensions. And so what you want to do is find a family of eigenfunctions, phi1, phi2, phi3, ... whatever. So in these coordinates, your infinite dimensional Koopman operator, if you project it onto this subspace of measurements, you get a 3x3 matrix. If I measure the world in phi1, phi2, and phi3, the dynamics of this are given by a 3x3 matrix, K, phi1, phi2, phi3. And so this is what you call a Koopman invariant subspace, so that if you take that subspace and hit it with the Koopman operator, you stay in that subspace. You're basically looking for eigenfunctions of the Koopman operator. Special functions that if you measured the system in those coordinates, everything would look like sines and cosines and exponentials. Very simple to say, very hard to do. Okay? And remember that Poincare theorem I told you about way back when in 1906 for the three-body problem. Poincare told us that even for relatively simple dynamical systems like the double pendulum or the three-body problem, there are not enough blackboards in the world to write down the solution in general form. They are, in some sense, irrepresentable. There's this notion in mathematics of irrepresentable solutions. And these Koopman eigenfunctions in general contain that information and more. And so these will also be irrepresentable in general for complex systems. But that is almost a textbook example of what we want to use deep neural networks for. Really, really, really hard to represent functions. Okay? So now there's a huge movement to start representing these Koopman eigenfunctions, these special measurement functions phi, in terms of these deep neural network architectures that have extreme expressive power and can get close to infinite blackboards. Even 50 blackboards is better than what I can do on a piece of paper. Okay? Okay, so the way you actually solve that x dot equals x squared eigenfunction, I'll just walk you through it very quickly. So you have your original dynamical system, x dot equals f of x. You want to find some function phi so that phi dot equals lambda phi. And what you essentially do is run just do the chain rule, and you get grad phi of x dotted with x dot, and based on x dot equals f of x, you substitute that in there. And you find this expression has to equal lambda phi. This is my partial differential equation in terms of phi of x. And I've run this by a lot of my PDE buddies, and they tell me it's very hard to find solutions of this, which confirms our experience that it's very hard to find solutions of this. Okay? But there is a relatively straightforward expression you can write down that has to be true for continuous eigenfunctions. Okay? And so what you can do in this x dot equals x squared example, where just f of x is x squared, so just replace this with x squared, you can essentially write down, first of all, you try to write down a Taylor series for phi of x, and you realize very quickly that you can't make the coefficients of the Taylor series work. So then you write down a two-sided Laurent series, and you solve for all the terms, and then you get e to the minus 1 over x. So I need to talk to Clancy and see if that's what he did. That's what I did. And now this is a homework problem in my intro math class for grad students. Like, it's simple. As long as you write down the problem statement, I have a dynamical system. I want to find coordinates where it becomes linear. And under certain limited assumptions, you can actually derive these coordinate transformations. Okay, is everyone with me so far? Is it clear why we want linear representation? Okay, everything in the world is easier if it's linear. Okay, linear equations are like the Disneyland of differential equations. It's just fun. Oh, actually, I don't know, there's lines and maybe not. You want coordinate transformations that make your system linear. And at least sometimes you can find them, but I would challenge you that these phi of x functions might be more complicated to write down and solve for than solving the original differential equation in the first place. So this is actually this makes a lot of sense in the machine learning framework. Finding phi is an offline computation. Google doesn't care how much it costs to find a better model that's 2% better. It might spend months on 100,000 GPUs to do it, almost infinite computation. But once it's found that, it can use it forever after and just rake in the benefits. That's how I think of Koopman operator theory. It's an extremely expensive one-time upfront cost to find phi. It's probably harder than anything you've ever done with that differential equation in the first place. It's like the hardest thing you can do with this differential equation in some cases is finding these coordinate transformations. But once you find them, everything becomes easy afterwards. OK, questions about Koopman operator theory? Yeah?
So, can you give us an example of something after you use that, your phi, that you could find much more easily than the original coordinate system? I'm just having a hard time understanding this line setting.
Yeah, so we're still developing this theory. So I'm going to tell you a mix of speculative and real, speculative fiction and facts mixed together. So something that we have actually used this for, once you find these phis, not we in the community, my group and other groups have done, you can then use these models for control. And everything in control is easier when you have a linear system. So the optimization to solve for the controller becomes easier. You can apply it in real time in cases where you can't necessarily do real-time control on this, but you can do real-time control on linear equations. So that's a huge example where finding this upfront, maybe it's extremely expensive to do it, but now I can actually use this in my robot in real time because I have a fast linear model. You can also imagine if I have these equations, I can do future state prediction much farther into the future because it's just e to the lambda t. Whereas future state prediction here means some complicated integrator. I can also do simpler uncertainty quantification in the linear regime than I would be able to do in the nonlinear regime. So this warped coordinate system can also simplify how uncertainty would spread through your system. People use it for nonlinear estimation. So those are just some of the examples that people have used this for. And I'm glossing over most of the details of how we actually compute these. I'm hoping during the actual workshops you hear lots more technical depth of the algorithm. So there's an algorithm somewhere between DMD, which I showed you, and this Koopman theory, where essentially what you do is, so what DMD does is it takes x, and it tries to build, I'm going to put everything in continuous time for a minute. It tries to build, x dot equals ax linear in the state. Or x at time k plus 1 equals a times x at time k. Let's make it like that. Discrete time. This is what it actually does. There's something called the extended dynamic mode decomposition, where you can build an augmented state of nonlinear functions of x. So it has x, and then these functions g of x, and maybe it's way, way, way bigger than the original state. And then you do a big regression, but basically it's just a DMD regression to find this bigger operator k. Did I say that too fast? Would anyone like me to say that again? OK, so DMD is basically doing a linear regression directly on the state of the system. My measurement in Koopman land is just the identity measurement on x. I'm just measuring the state. But what you can do is you can augment this vector with nonlinear measurements, x squared, x cubed, sines and cosines of x. And you can build a much bigger regression problem to find k. And so this is one approach. Frank Noe and others in his group, and Clancy Rowley, and many people have done this. It can be called extended dynamic mode decomposition, the VAC, variational auto conformation approach to conformational dynamics, VAC. So VAC, and this actually predates EDMD by a bit. But essentially, it's based on this idea of regression models to find relationships. And then if you look at the eigenvalues and eigenfunctions of K, you might be able to find kind of these special functions where the system behaves linearly. Okay, so I'm glossing over this. That's like a whole another lecture. Okay, I have 15. Yeah.
So this example is beautiful in some way in that there is a very, very easy to express function that makes all that you can find your phi that makes it all glorious. Is this the random exception where there's some nice closed form, or is there a belief that there's a lot of closed forms we just can't find?
So this is kind of the Goldilocks example in my mind. That's not to say that the method can't be applied to a broad range of systems. It can. So for example, in any Hamiltonian system, any system with a conserved quantity, that conserved quantity is a Koopman eigenfunction with 0 eigenvalue. Kind of cool. The Hamiltonian is a Koopman eigenfunction. Total angular momentum of an asteroid is a Koopman eigenfunction. So there are these kind of analogs even for very, very complicated systems where you do have special functions that you can write down and actually use those to derive other special functions. But I will say, again, I was sitting in this room at 2015 in United Technologies, sitting with a group full of Koopman people, and I told them, this sounds great, but I can't get Koopman to work on the pendulum. And I had tried really hard for weeks to get a Koopman embedding for the simple sine pendulum, and it doesn't work. And years later, we know why it doesn't work. It's because it has a continuous eigenvalue spectrum. So if you look at your pendulum at the down position, it has a resonant, it has its natural frequency. And as you increase the energy, that frequency gets slower and slower and slower until eventually it goes to 0 frequency at the top. Okay? So it's this whole continuum of frequencies. It's not a discrete set of eigenvalues. There's a continuous set of eigenvalues. Igor's known this forever, Igor Mezich, and kind of the math side of things. But for us practical engineers trying to find these, that was a huge obstacle for almost a decade. And now we're finally coming up with techniques to solve Koopman for continuous spectra systems. And so there's a lot of subtleties here for actually getting it working, but I do think we're coming to the point where it's getting useful. Yeah.
So what are the mathematical strategies, or are mathematicians still working?
Sorry, are there still mathematicians working? Many, and increasing numbers, yeah. There's also the kind of dual side of things and the Perron-Frobenius operator side, and there's a long history of people working on that as well. Okay, good. I am going to tell you about neural networks for dynamical systems. It's a little bit of a change of pace, and I'm only going to do a little bit on it. So neural networks to learn and represent dynamical systems. And I'm going to talk a little bit more about this when I talk about fluids. So that's on Tuesday. We're going to go a little bit more into depth on this. But I'm just going to start now. So the basic idea is that if I only have data of x, and maybe I can estimate its derivative from data, what I'm really trying to do is find some function that maps x to its vector field, its x.dynamics. That's what dynamical systems discovery means. And so you can use neural networks to do this, and many, many people have. And this is actually decades old work. There's work that goes way back on this. And so essentially what you're trying to do is build a function for the mapping between x and x dot. And then if you have that mapping, you can essentially integrate and step your state forward in time using some kind of an integrator. Here I've done the simplest, crudest forward Euler you could cook up. Or you could directly learn the mapping that steps your state forward in time at time k to k+1 to k+2 and so on and so forth. Okay? And so there's a lot of success in people using neural networks to build models for things like the Lorentz system and more complex dynamical systems that are chaotic, all kinds of interesting systems. Yanis Kevrakidis was here on the first day of the kickoff, and I think he'll be here throughout various parts of the program. And he did some of the earlier work that I know of decades ago using neural networks for time steppers for dynamical systems, back before we had deep neural networks and they were fashionable. So I'm going to show you an example. This is an example Nathan Kutz cooked up for our book, where basically he's trying to learn the Lorentz system. And he starts with a bunch of initial conditions to get some transients to see how these initial conditions rapidly glom onto the attractor and then move around. So this is the training data. And this is applied on 2 test trajectories here. Okay? And this neural network, it's just a simple feed-forward network. And essentially, it does a pretty good job of actually capturing roughly the attractor structure. But I will point out that the nearby trajectory does a good job. That's this one that looks like it's kind of shadowing the attractor. But if I go a little farther out past where I train my model, I get terrible results. In fact, it goes to this limit cycle, which is not Lorentzian at all. So these do have a big problem with generalization. So you really can use them for interpolation where you've collected the data, but not so much for extrapolation. Okay. Good. OK, this is a weird slide. There are other architectures, and I'm only showing a couple of the ones that have been used. Reservoir computing is like a very popular method now for simulating dynamical systems. There's been a lot of evidence that these can do a really, really good job of capturing even very chaotic dynamical systems for a surprisingly long time. Recurrent neural network architectures, like what Frank mentioned, seem very natural for simulating dynamical systems. Like dynamics are characterized by feedback at multiple timescales. And so LSTMs and other RNNs can be very useful for predicting dynamics. There's a great paper by Pantelis Vlachis and all I'd point you to. And then later in the fluids lecture, I'm going to tell you a lot about these autoencoders for taking high-dimensional dynamical systems and modeling them. And I'll show you work that Kathleen Champion and others have done using these to model dynamical systems of very high dimensions. I'm just going to highlight the work of Pathak and all on this reservoir computing. They were solving the Kuramoto-Shivashinsky dynamical system. So it's a one-dimensional PDE. This is the state of the system as it evolves in time. And what you can see here, I believe this is the true system, the modeled system with the reservoir computing, and the error instantaneously, and the error as you time step, as you run that through an integrator and use it just for prediction. And you can see that it actually does a really good job of predicting this thing way far. I mean, it's a very chaotic system. There's a lot of nonlinear mixing that's happening. And the error is actually pretty small for a long time. Very impressive raw prediction results. Now, in making black slides, it's kind of fun. You play around with the color bars a little bit, and you actually can see things in your data that you didn't know were there. So I actually have done this to some of our papers and see the exact same thing. If you change the color bars a little bit, you can actually see that there are some small errors accruing very early on in this, but it just takes them a while for the exponential growth of this chaotic system to kick in. Okay. OK, that's probably all I'm going to talk about neural networks for now. Like, this is a vast and growing field of people using neural networks to predict dynamical systems. One of the things that, some of the things I think are particularly interesting is we're not just trying to eke out a couple more percentage point of accuracy, like Google might be or Amazon. We care about things like stability and conservation and symmetry and constraints that are in the physics, that are in the actual system. So if I have a system that has a rank 1 saddle, I want that basic structure to somehow be in my neural network. And so there's a lot, I think a lot of the people in this room and a lot of the people that are going to be coming in for the various weeks of the workshops are going to be talking about how to embed structure into these representations of dynamical systems that generally are not designed to respect these structures. So you've already heard a lot about this. You're going to hear a lot more about it. A lot of the people in this room are doing it right now. That's kind of, in my mind, the cutting edge is learning how to bake in known structure, bake in stability, bake in conservation, symmetries, constraints, things like that. And actually, interestingly, if you just build a big neural network to represent a complex system, can you learn about invariants that you didn't know were there? Can you learn, these Koopman eigenfunctions often are near invariants of the system. Are there invariants of complex systems that I didn't know about? Is there a Hamiltonian for the brain and sleep state? interesting questions like that come up all the time. Okay, any questions about that before I go on?
Yep.
Yeah.
Can you briefly comment on how you would train in your network to represent these functions? So is there a specific lot?
Ooh, it's such a good question. I'm so glad you asked. Yeah, in fact, that's one of the most important parts is how you cook up the loss function, the training data, and the architecture. So you have a lot of choice in how to design these things. And what we found time and time again is that the simple thing we think should work doesn't usually work the first time. This is such a big question that I could probably tell you, at least half an hour or an hour of tricks that we've learned. Kathleen Champion is an expert and can tell you all kinds of tricks and things that she's learned in training these neural networks and others. Yeah, so maybe that would actually be a great, sorry I put you on the spot, Kathleen, but I think that would be a fantastic, like on one of the off weeks, for people to just share tips on how to train these things. I've learned some from Frank. I believe they call it Kolmogorov iteration. I think that's what you call it, where you basically, you're not actually just trying, this is a thing, you could basically take the exact same data from DMD, and you have your big X matrix and your big X prime matrix and try to learn the one-step forward network. That generally doesn't work as well as you also want to apply F a few times. Can't draw it that many times. But what I might want to do is apply that to X, K, and get XK plus 4. And so there's some, that's probably the most obvious thing that you would do is you would include in your loss function not just the one-step prediction, but multi-step predictions. But choosing that length of time depends on the Lyapunov exponent, it depends on noise, it depends on all kinds of things. It's a very big question, very good question. I hope that maybe that's something that could come out of this workshop is how do you do this? Yeah. Okay, I have 2 minutes left, so I probably shouldn't go into a big history on the parallels between Kepler and Newton and Galileo and all of the greats, but I will just show you some cool pictures. So Ptolemy, I'm lifting the Ptolemy part from Nathan Kutz, who does a better job describing this than I do. But the Ptolemaic system was essentially this idea that you could describe the motion of celestial bodies as basically a summation of circles plus littler circles plus littler circles. Does that sound like anything to anyone? So it sounds a lot like the Fourier transform to me. I'm adding up a bunch of circles of different frequencies. If you go to, this is supposed to be 2 different slides, but if you go to the Galileo Museum in Florence, you can have a view of, I think it's Santucci's armillary sphere. It's this beautiful nested Game of Thrones looking thing where you can use it to predict where stars will be. Does anyone know where this is from? For the younger ones in the audience, can anyone place it? The dark crystal, yes, good. So, these are beautiful structures, the prediction of the future and using it for prediction. This is a video my wife showed me, taken from 3 Blue, 1 Brown, which is probably my favorite YouTube channel. I'm going to kill the sound. But basically what it's showing is that you can use these complex Fourier series to essentially approximate any shape. So it's no surprise that you can use these to approximate the orbits of celestial bodies and ellipses very, very accurately. I love this video. This is just fantastic. This is pretty cool. But it's a little bit of an overfit. I think that's a very important point to make, is that circles on just Fourier transforming the star data is a pretty good way of overfitting your data, and it doesn't get to the principle, the interpretable, generalizable F equals MA model. I just love it, this incredibly complex pattern to build Fourier. Okay. Other things that I'll point out, there's this parallel between Aristotle and Galileo. So in terms of the ball drop experiment, this famous experiment where Galileo dropped 2 balls of different masses and they hit at the same ground. This is kind of fictitious, probably. Recently, we received data of balls being dropped off of a parking garage at different masses of balls. They weren't that well controlled. One is a basketball, one's a tennis ball, one's a wiffle ball, so they're very different. But if you this is a cautionary tale for blindly doing machine learning, and this is work by Brian De Silva and Nathan Kutz, is that if you just measured those trajectories and plugged them into your favorite machine learning algorithm, what you're going to find is that the rate of fall is absolutely proportional to the mass. Like, you will find Aristotle's, the Aristotelian view of mass and motion, and you won't ever get, the universal gravitational constant. And so the story actually goes that Galileo was sitting in a church, he was bored to tears, and he was looking at this pendulum clock and realized that that clock had the same period, regardless of he basically deduced the universal constant of gravity and the relationship of the period to length. And then what he did was he devised these extremely subtle and intricate devices. So he didn't drop balls off of the Tower of Pisa. He built these shallow ramps in still rooms with little bells at intervals so that they would ding, and he could write down the timing with a clock. So it wasn't, it wasn't this kind of simplistic story of just dropping balls. There was a very careful kind of process of epiphany and then careful experimental control to back out different forces. But if you just blindly do machine learning on this, you are almost certainly going to get the Aristotelian view of mass, and you're not going to get gravitational constants. And I'll probably not go through Kepler and Newton and Bray, but of course, again, you want models that generalize. You want the Newton model. Ellipses are great, they're useful, but they can't let you land on the moon. Okay, you need the generalizable F equals ma model. Okay, dynamical systems are awesome. I love them. I hope you love them too. We should talk more about them over the next weeks. All right, thank you.